Well, all right. Good morning, everybody. We're going to do a problem completion session. We're going to start here on problem 16.2 out of the handout. And the way that we'll work this, I do not have a formal lecture prepared. So what I'm going to do is I'm going to start working this problem, and your classmates that are here are going to interject when they have questions or additions, or if I start getting down, as I like to say, in the weeds with my arithmetic, because I don't want to carry on for 1,000 years before we get it straightened out. So let's come over here to the document camera, and I'm going to draw 16.2. And it says, for this simply supported beam, determine the stress blocks at point A and point B of the cut. All right, so what we're working with is a beam that has a fixed support here, a rolling support here, and as you notice, this is drawn a little bit differently. We generally have a rolling support that is only shown on the bottom, but the reason that we have it is because we have a 100-pound load pulling the beam up at this point, as well as a 200-pound load pulling to the right. But the fact that this load is pulling up means if we didn't have a rolling support on the top, that the whole beam would move upward instead of having a restraint and having a reaction here at point E. So the other question that was asked before we started streaming, is this support, the rolling support on the bottom, needed? And the answer is not really. The only thing that that does is, before the load is applied, keeps it level. But there's really no reason for it if there's a rolling support on the top in terms of this loading condition. All right, so this is point D, and this is point E. And we have 8 feet from each, a 100-pound load, which means, of course, that our entire beam is 16 feet long. And we are interested in a cut here 4 feet. This would be the cut face, 4 feet from point D. All right, so the first thing that we do as good engineering students is we do a free body diagram. We need to find the reaction at D and the reaction at E. Now, in the Y direction, you can see this by symmetry, that half of the Y load is going to be born here and half of the load is going to be born here. So if we were going to write this out, we could say summation forces Y equals 0, the reaction at D in the Y direction plus the reaction at E in the Y direction plus the 100-pound load, because it's positive, is equal to 0. And then we would get a statically indeterminate, or we'd get an overspecified equation, 2 variables, 2 unknowns in one equation. So we'd have to do another equation such as a moment equation, summation of moments about point E, for example, is equal to 0. But the upshot is going to be that the reaction at D is equal to the reaction at E, which is equal to 1/2 times 100 pounds, which is 50 pounds. And in both cases, those forces are going to be pulling downward. Now, this rolling support cannot support, that sounds weird, cannot bear a reaction in the X direction. So that means that all of my X is going to be born over here. So we also have an RD in the X direction, which summation forces X equals 0. Reaction at D in the X direction is going to be 200 pounds, pulling this way. All right, so there is my, the beginnings, that's my free body diagram. I'm interested in what's going on this cut face. So what I wish to do then is to just draw the chunk of the beam either from the left to the right to the cut face, or the other way around. And I choose this way because then all I have are my reactions at D in the equation. I don't have to worry about this applied 100 pounds. I don't have to worry about this applied 200 pounds. All I really have are my reactions at D in the Y direction, my reaction at D in the X direction, and then I have what's going on the cut face. All right, so I draw this as though it's positive. We would say the reaction in the X direction looks like this. The moment, positive, we draw like this. And then if you recall, when I'm cutting this way, my V force positive is drawn like this.
So just to start off,
Sure.
that we actually took the other side of the block. Is that a mistake?
No, it's just harder because you have more stuff going on. You would have to take into account this in your equations.
Okay.
You'd have to take this into account in your equations, plus you would have to take this into account in your equations.
We might have done that, but I don't think we drew that on the block. I don't know.
That would be a problem. That would be the first thing, right? Okay, what we want to do then is to find out what V, and I guess I should call this P, is what we've been calling it, like that, and moment. All right, so we say, on the cut face, the summation of forces in the x direction equals 0. I have minus r dx, which is 200 pounds, plus P equals 0. That means that P is equal to 200 pounds. So far, so good?
And so where V would be equal to 50 pounds?
Well, we have to do the math, right? Summation forces y direction equals 0. This is negative 50 pounds minus V, because as you see, we draw it this way to be positive, but it's actually pointing downward, is equal to 0. So that means that V is equal to minus 50 pounds. We then have this moment about the cut face. Summation moments on the cut face is equal to 0. This force pulls, if I anchored it, if I put a stick pin right here, that's going to pull it around in a counterclockwise direction. So this is a positive moment in the magnitude of 50 pounds times 4 feet plus this moment at the cut face is equal to 0. Because why is this positive? Because it's counterclockwise, right? So what does that mean? The moment then is equal to negative 50 times 40, which is 200 foot-pounds. All right. So now I know what's going on this particular cut face. The next thing I have is, I know then that my, what am I trying to say? My tau is going to equal VQ over IT plus or minus TC over J. There's no torque, so that goes to 0. My sigma is going to equal plus or minus P over A plus or minus My over I. Okay? And we have 2 points that are of interest. One is point B, which is on the neutral axis, and one is point A, which is 1/4 of an inch from the bottom. All right. Now, first of all, if you look at the equation for sigma, and you say my over I, y is the distance from a point to the neutral axis. So the my over I component at point B is equal to 0. Okay? So at point A, or let's say point B, sorry. This pen is running out. I'm going to look and see if I have a better, more dramatic looking pen. All right. So at B, tau is equal to VQ over IT, and sigma is equal to P over A. Now at point A, tau, I should do this, tau is equal to VQ over IT, and some of these terms are the same, so the V's are the same, the Q's are not the same, the I is the same, and the T is the same. But we're going to have to find different Q's. But here, sigma is going to equal P over A, then plus or minus My over I. Okay, so this I and this I are the same. So we have some math features that we can do before we get going. Okay, so, oops, there we go. So if we find, we know what V is, we know what T is, thickness, not torque, right, little t. We know what P is, and we know what M is. These are constants. It is the same at all points. But then we're going to have to find Q at point A, Q at point B, and Y at point A. Those are going to be my three things that change from point to point. All right? So I've already found what my V is, negative 50 pounds. T is the thickness of that cross section, which is stated in the problem, 1.5 inches. P is what we solved for with our summation of x equations. It's a positive 200 pounds. And the moment is negative 200 foot-pounds. Okay. Oh, I have to get my I value. That's the same. No, I'm sorry. I's over here because it's the same. I, because it's a rectangle, is 1/12 times the base times the height to the third, which is 1/12 times the base, which is 1.5 inches, times the height, which is 4 inches, raised to the third power. Which is, I get 8 inches to the fourth. Is that what you guys got?
Yeah, we did, but we had we just kept plugging it in. We didn't find I by itself, so we just have 12, 1.5, 4 to the third.
Understood. Okay, very good. All right, so now let's look at, I guess the next easiest thing to find is y of point A. So here's y of point A, which is the distance from the neutral axis to the centroid away from the neutral axis.
So I think we did that backwards.
Oh.
We're focusing the distance away, like it is offset from the, I mean, it's offset from the endpoints.
Right.
And so we had, strangely enough, for sigma b, we put A as 6 based off that, because it was 6 inches away from it, but I think it should have been applied to 0, right?
Well, that's correct. Well, okay, let me do that. The y of A is going to be, well, the way that I computed it was the distance from here to here, less half of the distance from here to here. So the distance from here to here, because the whole thing is 4 inches, this is 2 inches, and then subtract from that half of 0.25 inches. So that's your y value. But what is your q? Your q is equal to y times a, essentially. So it's going to be this value, 0.25 divided by 2, subtract that number from 2, gives you 1.875. Times the area, which is the width, 1.5, times the height, which is the distance from the point to the edge, which is 0.25 inches. So we take 1.875, multiply that by 1.5, and multiply it again by 0.25. And that value turns out to be 0.703, I'll carry it out, 125, that's in inches to the third power. Okay, similarly, Q of B, this whole distance, here's B is on the neutral axis, so this entire distance is 2 inches. Halfway down is 1 inch, so my Y is 1 inch, times the area, and that's the area of 1.5 times that entire height from here to here, which is 2 inches. So my Q at B is 1 times 1.5 times 2, which is 3 inches to the third power. Okay. So I didn't ever write that one down. 1.875 inches. Okay, there we go. Oh, that's not the, that's the y of a. That's for this calculation. But the y of a is the distance, the y that I use in the my over I equation is just the distance from the point itself to the neutral axis. And you know, this is the first time I've ever seen that those variables are different. So this is going to be 2 minus 0.25, which is 1.75 inches. All right. Now, what we need to do next is to compute our stresses. Tau at point B, which equals VQ over IT, and sigma at B, which is P over A. All right. So, and we'll talk about signs in just a minute. This is 50 pounds times my Q at B, which is 3 inches to the third, over my I, which is the same everywhere, 8 inches to the fourth, times my thickness, which is 1.5 inches. So if I look at my units, I have pounds, inches to the third, over inches to the fifth. That gives me pounds per inches squared, which is PSI. So 50 times 3 divided by 8 and divided again by 1.5 gives me a value of 12.5.
For which one? A?
Tau at point B. Now sigma at point B, we have P, which is 200 pounds, over the cross-sectional area, which is 1.5 times 4. I guess I didn't put that down, did I? The area of the whole thing is 1.5 inches times 4 inches, which is 6 inches squared. This is divided by 6 inches squared. So 200 divided by 6 is 33.3. Yep, 33.3 PSI. Now I know for a fact this is positive, right? Because it's in tension. Tau is a little bit squiffier, but we'll get back to that in just a moment. Let's go ahead and find our A stuff. Tau at A is also equal to V, but now we have a different Q value, which is 0.703125 inches, same I, which is 8, same thickness, which is 1.5. Okay, so we get, if I take those numbers, I get 50 times 0.703125, divide by 8, and divide again by 1.5. I get tau at A is equal to 2.93, and if you notice up here, same numbers, same units, this is PSI. And now for my sigma at A, I get P over A, which I know to be positive, but now I need to think about something. If point A is down here, and my moment looks like this, because it's negative, right? When I put it into this equation, I found that it was negative, meaning that it's really going downward. It is putting this point A into compression, isn't it? So that means that it subtracts minus my over I. So we get the same P over A value, which we calculated for point B, 33.3 PSI. And now we subtract from that our moment, which is 200 foot-pounds. So we've got a unit issue we're going to have to cope with in just a minute, times y, which is the distance from the neutral axis to point A, which is 1.75 inches, my over I, which is 8 inches to the fourth. All right. So when I look at this problem, I realize that the problem is the feet, right? So I have inches and inches. I need to change this from feet into inches. There's 1 foot per 12 inches. So I get rid of that, and then I have inches squared on the top, inches to the fourth on the bottom, which is inches per inches squared, which is PSI. So you have 33.3 PSI minus 200 times 1.75 times 12 divided by 8, okay? And so that becomes minus 525 psi. And so if I take those two numbers, I see that I get negative 491.7 psi as my sigma at point A. All right, so we're almost ready to draw stress blocks. The only other thing that we need to do is to decide, which was your original question, what is the direction of tau at point A and point B. All right, so what we do is, let's draw my stress block. Here's point A. Here is point B. Okay, here at point A, we know that my sigma is negative 491.7 psi. And we know that my value of tau is 2.93 psi. But the question is, what's the direction? All right, so I go back this way. This is my cut face. V determines the direction, because look at the equation. VQ over IT. Q, I, and T are all going to be positive. So V goes down. That means that I have to call this one my cut face, and V goes down. Now, I could have called this my cut face, and then V would have been down here, would have had to go up here, right? But so if this goes down, this goes up.
And then
That rotation, right, that rotation is clockwise. This rotation is counterclockwise. And that value is point A, 2.93 psi. Okay, same thing at B. If we choose this as the cut face, V goes down. So it looks like that. Tau at B is, I'm sorry, I gotta finish my arrows, don't I? There's all my tau arrows, 12.5 psi. And here, my sigma value is positive. Here it was negative, pushing in. Here it's positive, pulling out. Nope, sorry, 33.3. Okay. So there's the answer. Now, the other part is that choosing the cut face tells you where this goes down. If I had chosen my cut face here, it would have been exactly the opposite. And that just speaks to the nature of tau. The direction of tau is rotational, just like you knew going in. And so what it really means is this isn't going to rotate. Okay? So you choose it that way. All right? But as long as you're consistent, if you had the cut face on the other side, the arrow's going the other way, your answer is still correct.
Well, we seem to have gotten the sigmas correct.
Yay, good.
We were getting a bunch of that, but we did pick the wrong side, but the sigmas would have been the same anyways.
Super.
But our taus, when we were using our taus, we completely, if we were working off the packet or not,
Sure.
We knew the VQ over IT, but in there,
Yes.
either failed to mention, and we both forgot, but the plus or minus MY over I.
Ah.
That part. I mean, because we don't remember that part either, but, you know.
Right.
Again.
So that's right here.
Where?
Right here. Oh, shoot, you can't see it. Sorry. This is the second page of the handout.
Yeah.
Right there. See? So sigma equals P over A for axial load.
No,
Sigma
exactly. We
equals,
just didn't
right.
come to the conclusion that they actually could be
See?
combined.
And then, no, here you go, right here.
There it is, yeah.
Yep, there it is.
Oh, crap.
So, yeah.
Okay, well, we have to scrap that whole problem, but it's okay.
That's okay.
That's the point of learning, I guess.
It is, see? So, does this all kind of make a little bit more sense?
Yes. And that
Okay.
figuring that out, because we were getting confused if we determined the arrows based off the moment or the V.
Right.
We couldn't remember what it was. And from there, we know that the rest of our problems are problematic. But we do know, well, I think should we go through one of the other ones, the more circles? Because we feel like we actually were doing those correctly.
Good.
But then again, because of our numbers, it's going to be skewed, so maybe we should go with something that's independently more circle, so we know we're going through the process correctly, and then we'll just go and use that one.
Do you have a problem number you'd like me to work?
Yeah, then we have the one. 8? Yeah. 8.
Number 8?
8.
8 it is. For the stress blocks shown, determine the principal stresses. That would be sigma max and sigma min. The maximum shearing stress, tau max, and the angle of rotation for the vertical face to the closest principal stress. Super duper. All right, so here on the stress block, we have a sigma x is a positive 1800 psi. And we have sigma y. Oh, you probably can't see what I'm writing, right? So how we go. Sigma y is a negative 1000 psi. And tau xy is 4,500 psi. Okay. So what we need to do is to go back to sort of the steps, okay? And if you look, I'll find this. I know it's kind of dizzying to have me scroll through this really fast, even though I do it all the time. But here we go. The steps of the construction of Moore's circle. Find the stress block, check. Designate one of the faces as the vertical face, check. Designate one of the faces as the horizontal face, check. I just called this V, I could have called this V. I called this H, I could have called this H, okay? Then draw the sigma tau coordinate system. Remember, this is no longer X when we're drawing Moore's circle, it's sigma. And this is no longer Y, it's tau. Okay? Write the coordinates for the V face and the H face. The V face, the coordinates are going to be sigma, comma, tau. The coordinates for the X face are 1800 psi, comma. What kind of a rotation is this? Oops, I'm not showing you the right page here. I'm so sorry. Okay, so sigma X is this here. My rotation here is counterclockwise, so that's positive 4,500 psi. My horizontal face is negative 1,000 psi, and this rotation is clockwise, negative 4,500 psi. All right. Now, the stepwise directions say the next thing is to plot these 2 points. Vertical and horizontal are 90 degrees apart, right? What are they on Moore's circle?
Sorry,
That's okay. Vertical and horizontal in real life are 90 degrees apart. On Moore's circle, 2 degrees equals 1 degree in real life, so they're 180 degrees apart, meaning vertical and horizontal on Moore's circle are exactly across from each other through a radius of the circle. Okay? So for me, it's easier for me to find the center of the circle and the radius of the circle before I do this step. So I know that the center of the circle is going to be at, hang on just a second, sorry. And I mentioned this before, but Dr. Bailey does the rotations opposite. So he rotates positive is clockwise is positive, counterclockwise is negative. You can do that as long as you're consistent.
Yeah, we were wondering because when we had our Y's were backwards, but our
yeah,
X's were the same.
which you'll get the same idea. You'll get the same answers if you do it that way. So the center of the circle is at sigma x plus sigma y over 2 comma 0. We know that sigma x is equal to 1800. Sigma y is minus 1000 over 2 comma 0. This is 800 over 2, which is 400 comma 0. Right?
That's good.
All right. Now, for the radius, we get double parentheses. We have to have sigma x minus sigma y, not plus, over 2, quantity squared, plus tau xy quantity squared. Once again, because it's squared, whether you put in tau xy as a negative or positive, it does not matter. Then we have to take the whole thing to the 1/2 power. So my radius is going to be 1800 minus a negative 1000, which is plus 1000, over 2 quantity squared, plus 4500 squared quantity to the 1/2. All right, so my radius is 1800 plus 1000, which is 2800, divided by 2, quantity squared. And then I add to that 4500 squared, and that's this big number. And then I need to take the square root of that number, and I get a radius of 4713. 4713 psi. All right, so that means if my center, you can see it's going to be kind of a big thing, but what that means is the max point is going to be 400 plus 4713, and the min on the sigma axis, draw that, is going to be 400, which is the center, minus 4713. And so this is 5113, and this is negative 4313. Okay, so my center of my circle is like this. Obviously this is not really to scale, but I'm not very good at that anyway. So that means that this number is 5313, this number is negative 4313, my max is 4713, my min is 4713 negative. So if I take those points and I draw a circle through them, I have more circle. This is my principal stress, and this is my principal stress. Now the next thing I want us to do, I'm going to go back to the problem and take a look. It's number 8. It says determine the principal stresses, maximum shear stress, and the angle of rotation for the vertical face to the closest principal stress. Okay, well if I look at my vertical face, that's going to plot out at 1800 and positive 4500. That's my vertical face. 1800, and this is again not to scale, 4500, like that. What is the angle? This is my closest principal stress, isn't it? Okay, so the answer is, what does this triangle look like, and what is this angle? Well, if this is 1800 and this is 400, that means that this is 1800 minus 400, or 1400, and this is just the 4500. So there's my geometric construction. So my theta on Moore's circle is, I would say, the inverse tangent. The inverse tangent is, or tangent is opposite over adjacent. So the angle is going to be the inverse tangent of 4500 over 1400. Second tan, parentheses, 4500 divided by 1400, parentheses, equal. That gives me an angle on the circle of 72.7 degrees. That means that on the stress block, so I'm saying the angle on Moore's circle is 72.7 degrees. The angle on the stress block then is half of that, 36.6 degrees. 36.4 degrees. All right. How do I draw that? All right. What it means is, if you think about this, if I go from the vertical face, I rotate down to this principal stress. Which way am I rotating? That's clockwise, isn't it? So that means that from the vertical face to the stress block, or to the principal stress, I need to rotate clockwise. So the angle to the principal stress is 36.4 degrees, clockwise from the vertical face that I chose. Yeah, yes?
So if you were to draw like the block, like in the book they described that we were drawing the block where it actually was just the block angle.
Oh, okay. Let me see where that, I know what you're talking about. I just like this, but I know what you're asking me. So let me come over here. What you mean is like this, right? Okay. So what that means is that this is my vertical face. Well, let's go from here. If this is 36.4, because I really draw, if you want to draw it from a horizontal, that means that this angle is 90 minus that, which is 53.6 degrees. So if I draw a horizontal, we can't, let me see if I can widen this. Yeah. Okay. So what I did was I said if this angle is 36.4, this angle is 53.6, right? Okay. So if I want to draw that from the horizontal face, which way am I rotating? I'm rotating this way. So it would look like this. This angle would be 53.6 degrees, and this is where my principal stress would occur. So this would be the 1800. No, I'm sorry. 5113. And my tau would be whatever. Well, I guess you don't really draw the tau, so that's what I would. That's the way I would draw it. Now, the other way that they do this is they draw this as this is the principal stress, which means that that's this. So to rotate to the horizontal face, yeah, or to the vert, you would go the other way, and it would look like that. Okay? Yeah. So we got everything right except for the rotation of the block on actually how to draw it. Oh, good.
Yeah.
Good. That's very good.
So gotta fix that part.
Excellent.
All right.
All righty. Well, there you go, ladies and gentlemen. I'm going to turn off the streaming, and I'll boost this up so that we have it available if you need to go back through our work today. But I think we got some good ground covered. So there we go.